Welcome back to Logic. In this video, we're going to look at part 4 of natural deduction, covering the first set of the replacement rules for use with natural deduction proofs. De Morgan's is a rule that allows you to go from a negated conjunction to a disjunction of negations, or a negated disjunction to a conjunction of negations. So there's two versions of the rule. You can often recognize opportunities for using the rule because those propositions are so distinctive. A negated conjunction, where you have the dot in the parentheses and a tilde outside, or a negated disjunction, where you have the wedge in parentheses and a tilde outside. Or if you have a wedge or a dot that has both of its disjuncts negated if it's a wedge, or both of its conjuncts negated if it's a dot. So those are clues that this rule might be helpful for you. Let's look at a natural language example. Not both Star Wars and Star Trek are the best science fiction franchises. That is logically equivalent to Star Wars is not the best science fiction franchise, or Star Trek is not the best. Because not both of them are, that means one of them or the other has to not be the best. Intuitively, you can make sense of this rule by understanding what the negated conjunction means. It means not both. So if you know that not both things are true, then one or the other has to be false. Either the first one is false or the second one is false. Similarly, with the negated disjunction, that means neither nor. So intuitively, you know that if neither P nor Q are true, then both P must be false and Q must be false. With these replacement rules, you can go in either direction. That's why we're using a double arrow to indicate logical equivalence. You can apply the rule either starting with the negated conjunction, for example, and going to the disjunction of negations, or if you have a disjunction of negations, you can apply the rule and go the other direction. The reason why this works is because those two expressions are logically equivalent to each other. The next replacement rule is double negation. This allows you to go from a proposition to its double negation by adding two tildes in front of it, or in the reverse direction, going from a proposition that has two tildes in front of it and dropping those two tildes. So here's a natural language example. You're wrong that Jar Jar Binks is not the worst Star Wars character ever. That's logically equivalent to Jar Jar Binks is the worst Star Wars character ever. So you can notice in that proposition, you're wrong that is one negation and not is the second negation. So that's why it fits the double negation rule. Also keep in mind that there's no limit to the number of tildes or negations you can have in front of a proposition. So if you needed to, you could use this rule repeatedly, either to remove or to add two negations at a time. Commutation is a replacement rule that allows you to flip the order of disjuncts or conjuncts. So there's two different versions of the rule. Use the same rule for both cases. Here's a natural language example. Marvel Cinematic Universe is the best movie franchise, or DC Universe is the best movie franchise. That's logically equivalent to DC Universe is the best or Marvel is the best. And remember that this can apply both to disjunctions and to conjunctions. Intuitively, the reason why this rule makes sense is because the meaning of the disjunction or the conjunction doesn't change when you flip the order of the disjuncts or conjuncts. So for instance, if you said either I'm going to have eggs for breakfast or bacon, that's logically equivalent to saying either I'm going to have bacon or eggs. It doesn't make a difference, at least when the wedge is interpreted purely logically, purely truth functionally. Association is a replacement rule that lets you switch where the parentheses are, but only in cases where you have the main operator, the wedge, and one of the disjuncts is itself another disjunction, or when you have the main operator, a dot, and one of the conjuncts is itself a conjunction. So let's look at a natural language example of this. Either the Dodgers are the best MLB team, or the Astros or the Red Sox are the best. That's logically equivalent to either the Dodgers or the Astros are the best, or the Red Sox are the best. So I've switched around the order of some of the clauses there just to try to replicate switching around the parentheses in terms of how things are grouped. But logically speaking, those propositions are equivalent. It doesn't matter where you put the parentheses. The reason why we need parentheses here is just to make those compound propositions well-formed formulas, because we're only allowed to have one main operator. But if you look at the meaning of the wedge and the meaning of the dot, if you just have a long string of ors or ands, how you group them doesn't really matter. If you're using the and or the dot operator, you're saying that all of those conjuncts are true. If you're using the wedge or the or operator, you're saying at least one of those disjuncts is true. And it doesn't really matter how you group it. We just have the parentheses there as kind of like a convention of our logical grammar. Distribution is a replacement rule that lets you go from a conjunction that has one of its conjuncts a disjunction to a disjunction of two conjunctions. Or there's another version of the rule, a disjunction that has one of its disjuncts as a conjunction to a conjunction that has two conjuncts, both of which are disjunctions. Now this rule can be a bit tricky to remember and apply. A really helpful tip is notice the top version of the rule. The main operator is changing from a dot to a wedge. In the bottom version of the rule, the main operator is changing from a wedge to a dot. So you have to pay attention to the pattern of operators. Now, as with all these rules, you have to have the operators that are used to define the rule present in the example you're trying to apply it to. So if you had a case where you had a disjunction, one of whose disjuncts was a wedge, you might not be able to apply this rule because you have to have a case where it's a disjunction, one of whose disjuncts is a dot or a conjunction. So you have to pay attention to that pattern of operators. And like I said, the way for remembering the rule is that the main operator is always going to change, either from a dot to a wedge or from a wedge to a dot. So let's look at a natural language example. Apple makes good smartphones, and either Samsung or Google makes good smartphones. That's logically equivalent to either Apple and Samsung make good smartphones or Apple and Google make good smartphones. The reason why it makes sense to regard those as equivalent, if you look at the first version, you're saying that Apple definitely makes good smartphones. So that's true regardless of whether Samsung or Google also make good smartphones. And that's reflected in the second version of the proposition because you're saying either Apple and Samsung or Apple and Google. Either way, Apple is making good smartphones according to this proposition. And then you're leaving it up to the disjunction, well, either Samsung or Google also make good smartphones. So just keep in mind the pattern of the operators. Another clue with using this rule, I mean, like De Morgan's and some of the other rules, it's very distinctive in its appearance. So if you see a proof that has a proposition that's a conjunction, one of whose conjuncts is a disjunction, or a disjunction, each of which disjunct is a conjunction, that's a very distinctive appearance. Consider using distribution in that case just to see if it leads anywhere helpful. So here's a summary of the first 5 replacement rules. De Morgan's allows you to go from a negated conjunction or a negated disjunction to a disjunction of negations or a conjunction of negations, or vice versa. Double negation allows you to add or remove 2 tildes from a proposition. Commutation allows you to switch the order of disjuncts or conjuncts. Association allows you to move around the parentheses, but only if both of those operators are the same. If you have a wedge, one of whose disjuncts is a wedge, or a dot, one of whose conjuncts is also another dot. And then finally, distribution allows you to go from cases where you have a mix of a dot and a wedge, and you're moving around where the parentheses are, but you're also replicating one of those conjuncts or one of those disjuncts. So let's do some sample problems. In these first few ones, we're going to look at cases where we're just trying to fill in the blank. We're given one step of a proof. We know in this case that we're flipping around the order of the disjuncts from S wedge P to P wedge S, and we have to figure out which rule was used. So which of the first 5 replacement rules was it? It's commutation, or com. This is the rule that lets you flip around the order either of disjuncts or of conjuncts. Another practice problem. We have a wedge, one of whose disjuncts is another wedge, and we're switching around the parentheses around which operator. So which rule is this? This is association. Another example, we're moving from a conjunction, one of whose conjuncts is a disjunction, to a disjunction, both of which disjuncts are conjunctions. And you'll notice with this rule, we have the first conjunct of each of those conjunctions is repeated. It's the same. So that's another real telltale for this rule. The rule is distribution. So whenever you see the main operator shift from a dot to a wedge, and you either gain or lose a proposition that has either the first disjunct the same or the first conjunct the same, you should be thinking distribution. Another sample problem. This one, we're using distribution on a line of a proof. It's a conjunction. It has two disjunctions as conjuncts, and the first disjunct is the same in both cases. So what will this look like when we apply the distribution rule? Remember, the main operator is always going to change when we apply distribution. So the dot is going to change to a wedge. But also remember that the repeated disjunct is going to be consolidated. So the disjunct S is repeated in both of those disjunctions. So now it's going to become the first disjunct, and then after the wedge is a conjunction of the second disjuncts. So now we're applying the double negation rule to line 1. What will it look like after we apply double negation? There's actually two possible answers. One, we could choose to remove both of the tildes. That's the more likely case. There could also be cases where we have to add two further tildes in order to get to a conclusion or set ourselves up for another rule. If we use association on line 1, what would we get? Well, the parentheses are going to shift. So the main operator is still going to be a dot, but after we apply association, the main operator will be the first dot rather than the second. So now let's do some proofs of multiple steps. So in this case, we want to focus on the conclusion to see if we can get ideas for how to get that conclusion from those premises. The conclusion is a disjunction, the first of which disjunct is also a disjunction, parentheses L wedge M and parentheses wedge tilde R. So if we look for L wedge M, we can see that as the consequent of the conditional on line 1. If we look for tilde R, we can see that as the consequent of another conditional, this one on line 2. And maybe that will give you a clue to remind you of what rule we could use for this proof. However, if you're kind of stuck, you could always try just looking around at the premises themselves and seeing if they suggest any rules. Look at line 3. What rule does this remind you of, or what rule does this fit or resemble? The answer is distribution, and you won't always have to use distribution when you see a compound proposition like this that would fit it, but it can be a good thing to try if you're not sure how to go forward in the proof. It's very distinctive. We have a conjunction of two disjunctions, and the first disjunct of each of those disjunctions is the same proposition. That's distribution to a T. So let's try distribution on line 3. We get the main operator changes from a dot to a wedge. The S's are consolidated as the first disjunct, and the second disjunct is going to be a conjunction of the second of those two disjuncts, P and Q. Now, hopefully by now you've been able to figure out what rule we're going to use to complete the proof. You'll notice we have a disjunction, and the first disjunct S matches the antecedent of the conditional on line 1. The second disjunct P dot Q matches the antecedent of the conditional on line 2. So this should suggest to you the rule constructive dilemma. However, before we can apply constructive dilemma for this proof, we have to create a conjunction of lines 1 and 2, because the way the constructive dilemma rule is set up, we have to have a conjunction of conditionals. In this case, those conditionals are fairly complex propositions, so this creates a very long conjunction. But now we're ready to apply constructive dilemma on lines 4 and 5. Constructive dilemma allows us to move from a disjunction and a conjunction of conditionals, where the antecedents of those conditionals match the disjuncts. And we can move from another disjunction that matches the consequence of those conditionals, and that's exactly what we needed to prove in this case. So let's look at another proof using the replacement rules. In this one, the conclusion is not P or tilde P. So a strategy is to look for where we see this in the premises. You can see P in premise 1 as the antecedent of a conditional. So what rule could be used, at least in principle, to derive not P from line 1? The answer is modus tollens. So if we had the negation of the consequent, not parentheses q dot r close parentheses, then we could derive tilde P. Unfortunately, we do not have that. So here's where you want to strategize to see how you could build up the negation of the consequent in line 1, given what you have in premise 2. So the first step is to simplify out tilde q from premise 2. S is not going to be a part of the negation of the consequent of line 1, so we can just focus on tilde q. However, tilde q by itself is not really that close to tilde parentheses q dot r close parentheses. So how could we get closer to the negation of the proposition that we need? Well, if we remember that we could use addition to add a wedge and whatever we want after tilde q, this will allow us to get closer to what we need for modus tollens on line 1. We have to be strategic here. What goes after the wedge matters. In this case, we have tilde q wedge tilde r. We've introduced r on another line of our proof. However, this is not exactly the negation of the consequent, but what we're doing here is setting ourselves up for using another rule that will allow us to conclude tilde parentheses q dot r close parentheses. And that rule is De Morgan's. De Morgan's allows us to go from a disjunction of each disjunct being a negation to a negated conjunction, which is exactly what we need to set ourselves up for modus tollens with line 1. So the last step of the proof is just using modus tollens on lines 1 and 5. So this is a good illustration of how sometimes it is helpful to start with the conclusion and try to find it in the premises, but sometimes you will need to be a bit creative to figuring out what rules you can use together to get to the conclusion that you need. So another proof where we're trying to prove tilde P, and you can see again we have a conditional as the first premise, and the second premise is similar to the consequent of the conditional in the first premise. So if we had the negation of the consequent, we could prove the negation of the antecedent. This one is trickier though because the conclusion of the proof is supposed to be only tilde P. And if you look at the antecedent, it's not just P, it's P wedge Q. So you might be stuck, not sure how to get the conclusion directly from lines 1 and 2. Keep in mind though, if you're able to get rid of the consequent tilde parentheses r triple bar s close parentheses, then you'd be left with just the negation of the antecedent. You're getting rid of simple propositions r and s that are not a part of the conclusion. So if you're trying to prove something like tilde P, you want to work your way towards getting rid of the other irrelevant simple propositions and just focusing on the one that's in the conclusion. So a first step is to use double negation on premise 2. This creates the negation of the consequent from premise 1. And this sets ourselves up to do modus tollens on lines 1 and 3. So when we do modus tollens on lines 1 and 3, we can get the negation of the antecedent. Remember, the tilde has to go outside the parentheses because in modus tollens, we're negating the entire antecedent. In this case, it's a compound proposition, so we have to put that proposition in parentheses and have the tilde outside. So from here, we have to figure out how to get closer to just tilde P. And the form of line 4, the negated disjunction, should give you a clue as to what rule to use to help us get closer to the conclusion. And that rule is De Morgan's. De Morgan's allows us to go from a negated disjunction to a conjunction of negations. Now we still have that pesky tilde Q that's not a part of our conclusion, so there's one last rule we have to use to get to just the tilde P. And that is simplification, because that allows us to take one conjunct out of a conjunction. Let's look at another sample problem. This one we have one premise, it's a conjunction of conditionals. The other premise is a disjunction, and we're trying to prove the simple proposition M. So we can find M in the consequence of our conditionals in line 1, but they're embedded in all these compound propositions with a lot of different operators. You might be stuck in trying to figure out how you can get just M out of all that. So in this case, we have a clue just from the form, the logical form of premises 1 and 2. Premise 2 is a disjunction, and premise 1 is a conjunction of conditionals, each of which has an antecedent that matches the two disjuncts. So there's only one rule that this suggests. And that rule is constructive dilemma. Basically, premises 1 and 2 set us up for constructive dilemma. Now, you may be able to see where this is going. You may be able to figure out how we can use constructive dilemma to get M ultimately. But even if you weren't sure of how to proceed from here, it's a good first step. It's never a guarantee. The form of the premises will never guarantee, oh, this is the rule you have to use. But it's worth at least trying the rule that seems to fit the premises to see if it leads anywhere useful. Now, we have in line 3 a disjunction of conjunctions, and two of the conjuncts are the same. This should immediately suggest to you a certain rule, and that rule is distribution. However, in order to set this up for a distribution, we have to arrange the conjuncts so that the first conjunct is the same in both cases. So the rule we have to use to do that is commutation. We can flip the order of the conjuncts in the first disjunct, and then we can have the same conjunct M in both of our disjuncts. Now that we've used commutation, this sets us up for the distribution. So distribution can be used on a wedge where each of the disjuncts is a conjunction, and another requirement is the first conjunct has to be the same in both cases. That allows us to move from the wedge to a dot where the first conjunct is just M, and then the second conjunct is a wedge or disjunction of what was previously the second conjuncts. So now we've done this, we're basically very close to our conclusion. We have M as one conjunct of a conjunction. The second conjunct is L wedge Q. So it's one final step to get to the main conclusion. We can just get rid of the second conjunct we don't need using the simplification rule.